Now, why regression? Regression is more powerful than correlation because it allows us to model or investigate causal relationships. Relationships when we think one independent variable is a cause of a dependent variable. Regression analysis will, 1, reveal the precise nature of the relationship between independent variable and dependent variable. 2, test the null hypothesis that the observed relationship occurred by chance. And 3, provide a PRE measure of association between the independent variable and the dependent variable. To obtain a bivariate regression analysis, go to Analyze, go to Regression, go to Linear. We'll put the independent variable, which is a 10%, in the independent window or box. We'll go down and pick up the dependent, WimLeg 2015, that goes over, and we'll hit OK. Now, regression output features 4 tables. This one, variables entered, removed, model summary, ANOVA, which stands for analysis of variance, and coefficients. For our purposes, we'll only consider the model summary and the coefficients table. So I'm going to go ahead and delete the first table and the ANOVA table, and so we can look at the essentials here. First, let's consider the workhorse numbers down here. Here's the constant of the regression equation, 44.99. And here's the regression coefficient on percent frequently attending religious services, minus 0.535. What do these numbers mean? 44.99 is the value of the dependent variable when the independent variable is 0. So in a state in which there are 0 frequent attenders, the regression has modeled that to say that 44.99% of the legislators will be female. With every 1 percentage point increase in frequent attenders in the state, the percentage of female legislators declines by about half a percentage point, minus 0.535. Regression analysis is very precise this way. You can say, boy, that's putting a pretty fine point on it. That's the point. You can think in other units, though, if for every 1 percentage point increase in frequent attenders, the percentage of female legislators declines by 0.5%. For every 10-point increase in frequent attenders, the percentage of female legislators would decline by a little bit over 5 points. So we have a very precise model of the relationship here. Now, what would the null hypothesis say about all this? Well, the null hypothesis would say what it always says, that in the population from which the sample was drawn, this regression coefficient is really 0, and we got minus 0.535 by chance. Test the null hypothesis by looking at 2 numbers. This is the t statistic over here, student's t statistic, minus 7.097. We know by a general rule that when you have t values that have magnitudes or absolute values of 2 or greater, you have a significant relationship that would trump the null hypothesis. And here we easily exceed that 2 rule. We have a minus 0.707. And then the sig value, which is the p-value of that coefficient, minus 0.535, is 0.000. Under the assumption that the null hypothesis is correct, we would obtain a regression coefficient of minus 0.3535. 0% of the time, reject the null hypothesis. How strong is a relationship between frequent attendance at religious services and female legislators' percentage? That is answered by R square up here in the model summary table. Notice there are 2 versions of R square. There's R square, plain vanilla, 0.512, and adjusted R square, 0.502. We always use the adjusted value. It's more conservative than plain R square, and it takes account of sample size and the number of independent variables in the equation. What does it mean, 0.502? Of all the variation across states, which we just looked at earlier in the percentage of female legislators, we can explain about 50% of that variation by knowing one thing about states, the percentage of the state population that frequently attends religious services.